So besides the convergence ideas, we need a different concept, or we need another concept before we can talk about asymptotic normality results. And that's the notion of uniform tightness or boundedness in probability. So this replaces the usual notion of boundedness of sequences when you're dealing with stochastic sequences. So the definition is given here: a collection of random vectors xn is uniformly tight if this sort of technical condition holds, in which case we write xn as big OP of 1. Compare this with the little OP of 1, which was equivalent to, let's say, xn converging to 0 in probability. So the meaning of this statement is that the it's possible to, at high probability, contain the entire sequence within a compact set. So another way of writing this is that for every epsilon bigger than 0, there exists m such that with high probability, let's say at least 1 minus epsilon, we have say xn less than or equal to m. Or let's say, should say, m such that for all n, say for all n with high probability, or with probability, let's say, better way to write it is with probability at least 1 minus epsilon, we have that xn is less than or equal to m in norm. In the 1D case, this is just saying that xn belongs to negative m and n. So you can find an interval, a compact interval that contains the sequence. And this interval can be chosen to be the same for all n. That's the idea of being uniformly bounded. So with these stochastic statements, you can sort of think of this part, this this is the stochastic version. If you want to translate it into a deterministic statement, you would have like probability xn bigger than m is equal to 0. In which case this means that xn is less than or equal to m. So so for all n, basically, you would have something like that. So that's the stochastic version. That's the deterministic version. So the stochastic version allows you some leeway that this condition could be false, but the probability should be small, and that probability has to be uniformly controlled. So you need to, the uniform part is that the probability that they're outside negative m and m are all less than or equal to epsilon for all n, basically. So it can be that you fix this interval, and then for some of the members of the sequence, the probability is small, but for some, this could be getting progressively larger. Okay, so there are some results about uniform tightness. The first one is that xn, if you have a sequence xn that converges in probability to 0 and yn is uniformly tight, then the product is converging to 0. So this should be familiar for deterministic sequences, and this is the stochastic version. In compact OP notation, you'd say little OP of 1, which is xn, multiplied by big OP of 1, which is yn, is little OP of 1, which is to say that xn times yn converges to 0. So this is good to remember mnemonically. The second property which is a little bit more interesting, is that if xn converges in distribution to x, some random variable, then xn has to be uniformly tight. The converse, however, is not true. For example, the sequence that we discussed earlier, this counterexample, this sequence is uniformly tight. However, we can argue, or we argued, that this does not converge in distribution to anything. So convergence distribution is a stronger notion than uniform tightness. Okay, so that's the concept of uniform tightness that will come in handy later on.